So we looked at angles in a triangle, but what about angles in a circle? Okay, we need to be able to deal with angles greater than 90 degrees, and we can't accommodate that in a triangle very easily. So we need to use this model of a circle. And the way we need to be able to use this circle is we need a standard way of measuring the angles, and we're going to use this line here. This is called the initial arm, and we're going to say that that's 0 degrees, and we're going to measure in the counterclockwise the direction as positive, and down in the clockwise direction as negative. And when we put that point on the circle, we can see that this line here and the initial arm make an angle, and that's the angle that we're going to use for trig. And it does form a triangle here, but we need to reference this triangle a little bit differently, okay, because we have this same triangle showing up in different quadrants. So to be able to reference it correctly so that we can describe 360 degrees we need to use positioning. So we need to use x and y positioning. So we're going to just modify our definitions of sine, cos, and tan. So our SOHCAHTOA definition is going to extend in this way. So sine was opposite over hypotenuse, but now we're going to change the sine ratio into y over r. So if you take a look at this standard position angle, it's still kind of opposite over hypotenuse, where the radius is a hypotenuse. That still seems to make sense. So it's still in quadrant 1, it's entirely consistent with what we've done before, so no problem. And the big idea is that we want to connect sine with the y value, the vertical. The cosine we're going to redefine. Instead of adjacent over hypotenuse, we're going to say it's the x coordinate over the radius. And if we think of the right triangle, it's the same thing, the adjacent over hypotenuse. So it's not a stretch to do that, but it's key to recognize that the x now goes with cosine. Cosine is horizontal. And the tan is still going to be slope. So it's going to be y over x, or rise over run. So that's slope. So that's pretty straightforward. And the radius, we're going to calculate the radius the same as the hypotenuse. So it's going to be the x coordinate squared plus the y coordinate squared, square rooted. So everything in quadrant 1 is fairly consistent. Now, why we need to use x and y instead of adjacent and opposite is, it allows us to differentiate when we're in quadrant 1 versus when we start going to this quadrant here, into negative. So negative x and positive x differentiate the two quadrants. And this is important to do then, so that be able to go beyond 90 degrees, we need to use this positioning. So this is called standard position trig. And the x and y position describe the angle. So it tells you where you are in the circle. And that's very important. Okay, the triangle is useful. Okay, it's called a reference triangle, but the most important part of this is going to be the position. Which quadrant are you in? What is my x coordinate, y coordinate? Am I going positive and negative? Positive or negative? That makes a big difference where you end up in the circle, the position in the circle. So when we look at this, the position that I want is going to be this position here, the position on the circle. Okay, and the angle is going to be measured from this line, like that. And the positioning is given to me by a radius of 15 and a vertical positioning of 8. Okay, and that tells me that those two measurements indicate to me, gives me a point in space in this, on this circle, that locates the position of that point. Now we can also translate this to an angle. So the angle description of that position and the ratio description of this point are going to be the same. Okay, but we need to be able to translate between one and the other. They both describe the same point. Now to find out my angle from this ratio, well, this is when I need to use arcsine. Okay, so I know that my sine ratio, the sine of the angle that we don't know, is equal to the y position over the radius. And I'm going to color code this just to make sure that we can see that. Okay, because we really want to make sure that we connect the y coordinate with sine. So there's my ratio. Now I can see the position nicely here, but now I want a different description of that same position. I want the angle description of that position. So when I do this, I'm going to write it in my arcsine form. Okay, so this is just a way to use the arcsine form of this, and then I'm going to use my arcsine formula. So I'm going to do 8 over 15, and I want the arcsine of that. 8 over 15, and the arcsine of that is going to give me the angle of about 32.23 degrees, and that looks about right. Okay, so this ratio description and the angle description seem to be consistent. And again, try to understand that the ratio and the angle are describing the same thing. It's describing the angle of that triangle. Okay, and we need to use our calculator to just be able to go between the two. So this is in quadrant 1, so that's kind of straightforward. What if we go out of quadrant 1?